So my name is Philippe Specht, and I also work at the Chair of Theory of Hybrid Systems at RWTH Aachen University, and I will talk about our nonlinear research. So let's get right started. I want to keep this more on an intuitive rather than like a definition formula-based level. And therefore, we'll go right ahead with an example. And what we look at here are nonlinear polynomials. So assume we're given these polynomials, and what we're interested in is their roots. So what I got down here is the root plot of these polynomials. It can be interpreted as follows. So if I were to insert any of the points on this line into P2, it would evaluate to 0. In any other case, it would evaluate to something non-zero. For the purposes of this talk, I will omit this labeling, and I will also sometimes refer to these lines as only being P1, but remember that those are actually roots and not the polynomial itself is considered as a function. And also I will blur them out a bit, because when we later on look at algorithms, it should be clear that this plot is just for us and is generally not computable. So not for all nonlinear polynomials, it's easy to compute and display. So this is just a visual reference for us. Okay, with that out of the way, let's get right started with what single cell construction is. So given a set of polynomials and additionally a point S in this space, our task with single cell construction is to construct a connected sign invariant set containing this point. The biggest possible cell that we could find right here would be this space right here. And it's clear that it is connected, but what does it mean to be sign invariant? So when we evaluate our point S on all of these polynomials, we get these signings here. We get either greater 0, smaller than 0, and it could also be equal to 0. And if I were to pick any other point from the cell and would insert it into all of these polynomials, the same signing would come out. And it's the biggest possible cell because every other point that is connected to the cell would either be on the line right here on P3 or on P2. So the polynomial would evaluate, one of these polynomials would evaluate to 0, which would be a change in signs. So the cell wouldn't be sign invariant anymore. Let me formalize this real quick. So when we're given a finite non-empty set of polynomials in n variables with rational coefficients, which are non-constant, and a point in space, our goal is to construct a cylindrical algebraic cell that contains S. But because I don't really want to go into the definitions of being cylindrical, I'll reduce this to saying we want to construct a connected sign invariant set that contains S. This is not equivalent to the prior definition, but it's the essential part for the application of single cell construction. And therefore, we'll just go with this for this talk. Just as a side note, I will also assume this variable ordering throughout this talk. So x1 is the smallest variable always, and xn the greatest. And when we have this given, we can define the level of a polynomial as the smallest I, so that xi appears in P. This essentially transfers the notion of the dimension for spaces to polynomials. So the dimension corresponds to the level. So where can we now apply single cell construction? Generally, we can use it for SMT solving the first order logic theory of quantifier-free nonlinear real arithmetic, or short QFNRA. This is defined as can be seen here. So we have constraints where we can compare a polynomial in n variables with one of these operators to 0. And these variables can be of real values. And now the question is, when we're giving a QFNRA formula, so a Boolean structure containing literals of this form in constraints in variables x1 to xn, can we find such an assignment as 1 to Sn in real space so that f evaluates to true? And one way of going about this is by using MCSAT, which was introduced by Jovanovic and Demura in 2013. And this is just a framework, so we can actually use different things in there other than single cell construction, but single cell construction can be used in this context. So the way MCSAT works is essentially by finding an assignment as seen on the last slide. So this assignment is constructed step by step. And if at some point we get an unsatisfying assignment, we can use the single cell construction to create this set of unsatisfying set of points that are also sign invariant and therefore also unsatisfying, and we can then exclude this space from our search. And this is where we can use single cell construction. It's also worth noting that single cell construction is the computationally most expensive part of the of an SMT solver if it's based on MCSAT. And also, yeah. And the next thing I want to talk about is projection. This concept is used in the context of single cell construction and is the computationally most expensive part of single cell construction, and thereby also by transitivity also of the SMT solver that we construct with single cell construction. And therefore we will later on also optimize this projection to get better results with our SMT solver. So what is projection? For projection, we generally use a projection operator. This is nothing more than a mapping from polynomials of level n to polynomials of at most level n-1. This on itself does not do a lot. You could define something very trivial very easily. But if we actually have an additional property fulfilled by such an operator, so that the roots of these polynomials are are mapped in a way that the roots of these polynomials are somehow reflected in these polynomials, then we can use this for our purposes. And one operator that does this is McCallum's projection operator. And this projection operator has the following components. So when we're giving a set of polynomials of level less or equal I, we first of all carry over all the polynomials that are of level less than I, since they are already, they do not need projection yet. And if they are of level I, we first of all take the discriminant with respect to xi, giving us a polynomial of level at most xi-1. We then take the resultant between every two polynomials of level I, giving us again a polynomial of at most level xi-1. And we take the set of coefficients when considering the polynomial of level I as univariate over xi, so we receive a set of coefficients. And now I want to exemplarily go over all these components and show you what I meant by this property that we get that guarantees us that we can actually find cells, or rather that we map meaning from a higher level to a lower level. So what we can see here is the roots of P2, and we also have the roots of the discriminant right here. And what we can see is that the discriminant has its roots projected along the x2 axis, where the roots of P2 have a turning point. And in this case, this already guarantees this property I was cryptically talking about. And this property is that when we look at the intervals that are defined by these roots right here, so for example, if we look at the interval between those two roots, if we take 2 points at random from this interval, we will always have the same ordering of roots above this point in this direction that we projected along. So this means that for every point there will be no root, then there will be a root, no root, root, no root. And this precisely changes when we come to this point, which is the next point interval, where we have no root, root, no root. And then we get this open interval where we only have no root. And this essentially guarantees us that later on we'll receive proper cells, or we get information on the lower levels when using projection on polynomials. So the next component was the resultant. This works similarly, only that in this case, what we project are intersections in the roots of two polynomials. So we insert two polynomials here, and the resultant will have roots below where these polynomials intersect. And last of all, we have the coefficients, which have roots where the roots of polynomials tend towards infinity, because at this point, the order of roots does also change. Okay, with that out of the way, we can actually look into the concept of level-wise single-cell construction. As the name suggests, it is level-wise, so we go through level by level, starting on the highest level right here. And the process is always the same. So we start with our set of polynomials, which are currently in variables x1 to xn. And what we do then is we substitute in our given point up to the last dimension so that we have univariate polynomials. And the good thing about these univariate polynomials is that we can actually isolate their zeros in contrast to these polynomials, which is not generally possible. And this gives us this ordering of roots right here. So we have our roots. And if we then insert the last missing dimension of our point, we can use these roots right here to define the bounds of our cell in the nth dimension. How this looks more precisely, I'll show in just a second, but let me just first go through the algorithm. So the next step would then be to project. And the projection gives us polynomials of level at most n-1, and we can then do the same thing. We substitute the point up to n-2 so that we have univariate polynomials, isolate the roots, and then find the bounds that are closest to the point in this dimension. And we do this level by level up until we reach the last level, where we do not even need to substitute a point anymore, and we isolate the roots, and we get our cell description via these polynomials. Okay, let's look at this along our example. This will clear up a lot of things, hopefully. So we have the roots of P2 and P3 right here and our point. And right here is our cell description. So far, it's not filled out. We do not know what the upper and lower bounds are. And we'll start by determining the second dimension first and then the first. And as seen in the algorithm, we start by evaluating our polynomials in the first dimension, or up to the second. So in this case, this means only inserting the first dimension, which essentially means for the plot, taking all the roots that are on this line. So we get these roots, and what we can essentially see here in what we can see here vertically is what we've previously seen horizontally on the last slide in the upper right. So yeah, but these roots itself right now are just points in space, and those don't really allow us to define a cell really. And that's why we describe the cell symbolically using what we call root expressions. And this expression means that we take the first root of the polynomial P2 when evaluated up to the variable x2. This then in turn is the first root of the polynomial P3 when evaluated up to x2. And this is the second root of polynomial P2 when evaluated up to x2. And also, as seen before, we now take the bounds that are closest to our point in this dimension, which is this as the lower bound and this as the upper bound, and we insert those right here. And then the next step would then be to project our polynomials. I cannot really visualize this here. But what I can visualize is the roots of the polynomials that we just projected to. So isolating those would be the next step then. And we've previously also seen where these roots are, because this root right here comes from the discriminant and is here because of this turning point. We get this root right here because of the intersection of roots of polynomials right here. And we get this again because of the turning point here. Equivalently, we could also consider the intersection right here. So this could also be interchanged with the resultant. Yeah, and now we again consider the bounds, or we try to determine them, and we take the closest lower bound and the closest upper bound, which are those two bounds, and we insert them into our cell definition right here, symbolically describing this cell, which can be seen right here. Okay, so much for the level-wise approach. There's also been another approach that we took some inspiration from which we call refinement-based single-cell construction, which was published in 2015 by Brown and Demura. And this approach works a bit differently. So this approach works by initially stating that the cell is just the entire space. In this case, it's the R squared. And now we use iteratively pick all the polynomials from our initial set one by one and merge them. And by merging, I mean we refine the cell using this polynomial. So we use this polynomial P1 to refine the cell, cutting it short so that it's only this part. We would do the same thing for P2, but note that now this part also disappeared. And this is because this merging operation actually works recursively. So when you see our approach, it can somewhat be seen as breadth first. So we are always going through level by level, going into the breadth first. And this approach is kind of depth first. So when I say we merge P2, what we actually do is we first project P2 all the way to the lowest level. And then when we backtrack back to the top, then we use each of these projection results to refine our cell. Meaning that in this case, we would also need to consider when merging P2, we also consider the resultant of those two polynomials, which gives us this intersection right here, which cuts our cell short right here. And then continuing, we would merge P3, and this leaves us with this cell right here. And as you might have noticed, this is actually different from what I've shown for the level-wise approach. And if you paid really close attention, this is actually due to the fact that I omitted P1 for the previous example on the level-wise approach. And if we were to use P1 in the level-wise approach, and we were to use the McCallum projection operator as I presented it, then we would actually receive the same result as right here, but we can actually make it so that our cell does not lose this space right here, but is in turn bigger. And exemplary, we can explain this by saying that we can omit the resultant between P1 and P2 because their intersection is uninteresting to us, because neither of them define the upper bound. So they have roots above this upper bound, but neither of them are the bound. So if one of them would cut the bound, then it would be interesting to us, because then it would interfere with our cell. But since neither of them is the bound, we are sure that their intersection will always be outside of the cell. But but it's also worth mentioning that if we were to, for example, change the order in the refinement-based approach to first merge P3, then P2, and then P1, we would also get the same result as right here. So they also make it so that they do not consider this in the refinement-based approach. But the problem is that in the refinement-based approach, this is dependent on the order in which we are merging the polynomials. And as far as we looked into it, there is no really smart way of going about this. We have no points to find a smart heuristic for this, at least from what how we looked into it. But for the level-wise approach, this is different. And this is due to the fact that before we project our polynomials, we always have this entire root ordering. And on this root ordering, we can define which resultants we want to take in the form of heuristics. And into these heuristics, I want to look into right now. The first one is what we call the biggest cell heuristic. And what I displayed right here is such a root ordering as before. For simplicity, I'll say that this root C1 comes from the polynomial P1, C2 from P2, and so on. And there's only one root present per polynomial. And what I displayed with these arcs then is that we take the resultant between the polynomial where this root stems from. And the resultants that we take are then first of all between the lower and the upper bound, and then between the lower bound and between every polynomial that has a root below it. This essentially omits taking the resultant between two polynomials of which neither are the bound, because if they were to intersect, it would be outside of the cell, And if they were to intersect into the cell, this would already be covered by taking the resultant with the bound itself. So we do not need this anymore. And this approach is actually theoretically founded. So if we make some ideal assumptions, this is actually guaranteed to give us the biggest possible cell. But since these assumptions are somewhat unrealistic, we cannot just use this heuristic as being the optimal. So it remains to be a heuristic. And that's why we also looked for different approaches. Like, for example, the lowest degree barriers heuristic right here, which is more practically founded. So what this approach tries to achieve is to minimize the asymptotic complexity of resultant calculation. So when calculating a resultant, it is complex as follows. You take the product of the degree of the first polynomial in xi with the degree of the second polynomial in xi. And I displayed the total degree that corresponds to the polynomial P1, for example, in this case right here, and listed them right here. And the way we proceed now is by, first of all, taking the resultant between the upper and the lower bound. We really can't get around that. But then we look, for example, below this lower bound for the lowest degree, which in this case is this degree right here. And then we do, instead of considering this as our barrier, as seen previously, we consider this as our first barrier and take these resultants right here. And then kind of in a greedy fashion, we continue with our remaining polynomials that are not connected to our bound yet and take the resultants here so that we also guarantee that this bound does not get violated. Yeah, for above, this works similarly. We first of all take the resultant from here to here, and then the search is only on this polynomial, so we take this resultant right here. Okay, and in practice, this also works really well, just like the heuristic we've seen before, and we thus tested this. And the way we went about this is by putting this into an SMT solver that is based on this NLSAT framework that I talked about earlier. We implemented both NLSAT and the single cell construction approaches, both refinement-based and level-wise, in our SMT toolbox SMT-Red. And then we let the SMT solver run on the benchmarks contained in the SMT benchmarks QFNRA library. And these are results that we got out of this. So the refinement-based approach roughly solved 10 less, not roughly, it solved 10 less formulas than the best heuristic we could come up with for the level-wise approach. And when we now consider, first of all, the intersection of those two sets of formulas, so only problems that both solved, and then also omit problems in which single cell construction wasn't used. So this can happen because we are looking at an SMT solver based on this framework, and if it can happen that if the example, if the formula is easy enough, NLSAT can actually solve it without single cell construction, then we are only left with roughly 4,200 formulas. And on this, we get these solving times, which corresponds to a decrease in solving time by 7%. This is not very significant, but it's at least nice to see that we can find a strategy. Yeah, if we get a heuristic that we consider to be smart, it can work better than a refinement-based approach. Okay, to summarize all of this, the single cell construction deals with constructing a cylindrical algebraic cell around a given point. We've seen that this can be done in a level-wise or refinement-based fashion. For future work, it is even imaginable to use a hybrid approach. Then we look into the concept of projection. Since this is the computationally most expensive part of single cell construction, we want to optimize this. And the level-wise approach just suggests to optimize the resultant specifically because of this value of information that we have by doing it in a level-wise manner. And lastly, we saw that we can employ single cell construction in an SMT solver using, for example, the MCSA framework. And in our testing of these solvers against each other, we saw a decrease in solving time by roughly 7%. Okay, that's about it from me. Thank you for your attention. I can show you my references right here. If you're interested in any of them specifically, then ask for it. Otherwise, I will leave this slide on right here.
I think if you could show the references, it might help people, but
Sure.
That's up to you. Yeah. Thanks very much for that. I'm very intrigued. Your slide of results, which show that the intersection between the two sets of solves was really quite small. Do you have any feeling for which sort of problems are better suited for which approach?
Oh, this is actually really, really hard to answer. So the answer is no, I don't really have a feel for that. And that is because we can make lots of observations about the first level. So when we have, for example, like right here, only two-dimensional polynomials, we can actually make quite good statements. But the lower you go on the levels, the more times you will project projection results, and it will be harder to actually predict what's happening on the lower levels then. So that's why we are only using heuristics and do not really have one determined way that actually works perfectly.
Okay, so are you advocating a sort of polyalgorithm approach?
I'm not sure what that means.
But you might try both of them and see which worked.
Yeah, this is the way to go about it right now. So we don't really have any point of reference of which one is better. Complexity-wise, they calculate the same amount of resultants. So this doesn't really change. We just have a choice in which we're calculating.
Right. Okay, good. I see a couple of raised hands. Unfortunately, I can't see who's raised a hand. So could one of you with their hands raised please speak?
Yeah, I had just a quick question. Can we go back to slide 15 with the results? Maybe you said it and I missed it, but I'm not sure. So the results you're quoting for level wise, with which of the two heuristics are these results?
These right now are actually so there's something I left out here. So we actually need to make a distinction between two cases. So we can actually use okay, to answer this short, we use two different heuristics in this case for two different cases. The first one was comparably to this biggest cell heuristic, and the other one was a heuristic that is not shown right here, which we call somewhat chain heuristic, which just takes a chain as seen here. On this side, we would do the same thing on the other side, and this is what's taken in the second case.
Okay, so because this slide is comparing the level-wise approach with the approach from 2015. So are the times on this slide for the bigger cell heuristic or for the other one?
Okay, so we need to make a distinction because there's a difference. In this case, I only described an open cell, and an open cell has open bounds in both directions. But it can also happen that that our point is on a line, for example, so that a polynomial is actually so that we don't get bounds of this form, but we get bounds of where there is an equality here. So we can have a root be equal to x2 right here. And we actually have a heuristic that quite certainly works best for this equality case, which is the analogous thing to the biggest cell heuristic, which we call equational constraint heuristic. And this was used for this, what we call section case. And in the case of having open bounds, we used a chain heuristic, which is what I mentioned earlier.
So your implementation changes heuristic based on the nature of the cell that it's studying at the time. Okay, that makes sense.
Yeah.
Thank you. I see Martin has his hand up, so I'll pass over.
Yes, one quick statement first. So there's going to be an SC Squared business meeting after this session. And I've just put the address of that in the chat, which you might want to call up so that you can get there. Okay, Martin, you had a question. Martin?
Hi. Regrettably, I don't actually have a particularly good question. That was from a previous talk, and in the virtual world, you don't know your arm. Notice your arm getting tired. One thought though was that if the thing that James commented on of about a large difference between the classes of problems solved by different heuristics, that to me is a very encouraging sign, because it suggests that in total a large number of things are solvable. It's just a case of like maybe finding a heuristic that balances or matches or combines the two. So I would see that as a very positive sign. Diversity is good.